So it's a very different approach in physics where you're taking disparate phenomena and saying these all relate to the same thing. Whereas other sciences tend to take sort of similar things and break them down and micro divide them based on all their characteristics. But anyway, that's Newtonian gravity. So all of these different phenomena in the universe are just gmm over r squared. By the late 19th century, there were some issues that started to be noted. The planet Mercury wasn't returning to exactly the right point in its orbit. Ridiculously small amount, 43 arc seconds per century. I mean, I'm amazed that in the 1800s they could measure something like that, but they could. There were a few other things as well, and they were realizing that this Newtonian classical physics seems to have some problems. So they started putting some band-aids on it. They started doing little corrections, taking your Newtonian formulas and adding little correction terms at the end that are like expansions of v over c, the velocity over the speed of light. In general, these things only start to matter when you're going really fast near the speed of light, or when gravitational forces are very extreme, or if you're trying to make really, really precise measurements, parts per million, parts per billion accuracy, you start to notice these little deviations. So people added these little correction terms onto the end. It's kind of like when your roof leaks a little bit, you put a patch here and there. Well, eventually you get to the point that there's more patches than roof, and you decide, okay, now I have to just replace the whole roof. The guy who came around and did that was Einstein, who in 1905 said, we have to reimagine this whole thing. Gravity is really very different. It's not a force between distant objects. Instead, it's space-time itself is curving. So that idea that we have intuitively that space-time is sort of like a piece of graph paper, right? If I hold up a piece of graph paper, I don't have one here, but here's an envelope. If I take a piece of graph paper and I pull on it, I can't stretch it, I can't bend it. It has the shape that it does. Einstein said, no, space-time is actually not like that. It actually stretches. It's more like a rubber sheet. And you can think of it more like a trampoline. If I put a bowling ball on a trampoline, it causes the trampoline to have an indentation in the center, as what's kind of shown here. Now, if I took a marble or something and I flicked it along that surface, it's not going to travel in a straight line. It's going to travel in a curved path. It's going to curve towards the Earth as it goes around it. And that is gravity. It's objects trying to travel in straight lines, but on curved space-time, which is bent, and those lines appear to be crooked. And that's, in fact, what gravity is. Or a very simple way to summarize this is that mass tells space-time how to curve, and the curvature of space-time tells masses how to move. Now, that's a very, very simple way of looking at it. In reality, it's very, very complicated. If gmm over r squared is giving you a hard time, you don't want to see the equations of general relativity. They are absolutely, absolutely horrid. In fact, even Einstein, it took him 10 years to establish these equations, and even he couldn't find many solutions to it. It was people later like Schwarzschild and Kerr and Kip Thorne who were able to finally start producing solutions to Einstein's equations. So anyway, as I said, under normal conditions, both Newtonian and Einsteinian gravity make pretty much the exact same predictions to within parts per million, parts per billion precision. Or put another way, you can build a damn good bridge or a damn good airplane using Newtonian mechanics. And Newtonian mechanics turns out to be way, 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 way simpler than doing everything using Einstein's model. So for that reason, we typically still use Newtonian mechanics unless it's really necessary to go into general relativity. And that's what happens under these extreme conditions. So we're talking about black holes, neutron stars, things like that. Now, moving ahead a little bit, one of the solutions that pops out of these Einsteinian equations is that static spacetime is unstable. That in addition to being curved and bent by masses, spacetime will either tend to expand or contract very, very rapidly. Now, back in 1915, Einstein looked at this and said, no, that's ridiculous. The universe is stable. The universe is not exploding. It's not collapsing on itself in a fraction of a second. So when he was solving these equations, if you've ever taken calculus, you know that when you do an integral, there's always that plus c. There's that constant of integration that hangs off the end. Or sometimes you'll have initial conditions in mathematical systems. Well, in general relativity, there's a bunch of these constants of integration. And one of these, which was lambda, you have to come up with a whole bunch of letters. Eventually, you run out of English letters, so you have to switch to the Greek alphabet. One of these was called lambda, and Einstein noted that if you set it to exactly the right value, it cancels the tendency of space-time to expand or contract. So he said, aha, this is easy. We'll just set lambda to whatever value is needed to cancel out that expansion or contraction. We have static space-time. The universe is safe. Great. And this became known as the cosmological constant, essentially because it holds the cosmos constant. Then a funny thing happened. In the 1920s, Edwin Hubble noticed that distant galaxies were moving away from us. And that means the universe is actually expanding. So Einstein right away realized that he made a big mistake, that his equations actually predicted expanding space-time, but he didn't realize it at the time. He described this as his greatest blunder. I would say this is probably his second greatest blunder. There is a bigger one that I'll get to later on. So anyway, space-time is expanding. But what does it mean, and how do we know this? And by the way, if that data looks kind of sketchy to you, it is. This is what more modern data looks like, quite a bit better. But anyway, the universe is expanding. Now, I'll go through this fairly quickly because Mary Lou, I think, gave a good introduction to this last week. If you take light from a star and you break it up into its component colors, what you'll find is that at very specific wavelengths, you'll find either dark lines or bright lines. And these are like fingerprints of individual atoms. Remember, our atoms have these discrete energy levels, and I'm going to get to this later in the talk when we talk about small-scale physics. Atoms have these discrete fixed energy levels, and when electrons jump back and forth between them, it will absorb or emit a photon at a very characteristic wavelength. So when I look at a spectrum, it's like looking at a fingerprint. When I look at this, I can tell you what elements are present. Like I know that these two close lines in the yellow, that's due to sodium. This line over, let's see, 656, that's due to hydrogen. There's another one here at 486, that's also due to hydrogen. There's a few that are due to helium and so on down the line. So if we look at a star, we can actually tell what chemical elements are present. We can also make estimates of the temperature. We can make estimates of the pressure. We can also detect electric fields, magnetic fields, the strength of the gravitational field, because all of these things have very characteristic effects on the spectrum. And this really relates a lot, because what we can do is we can take the spectra of stars and we can directly relate that to spectra that we measure in the laboratory. We can take gases, heat them up to high temperatures, measure the light they give off. We can put it in a magnetic field, put it in an electric field, high pressure, low pressure, high temperature, low temperature, and you can see how the spectrum changes. So you can make a direct comparison between things that occur in the lab and things that occur on distant stars and even distant galaxies. And not just what's there, but also temperature, pressure, magnetic field, all of these other things. So this brings us to kind of this Law and Order picture. By the way, this is my favorite Law and Order, the original with Jerry Orbach. So what makes everything that we're going to talk about possible is the very same laws of physics which govern the phenomena on Earth, these things that we can observe in real time, are also at work elsewhere in the universe. And we can compare these things that we see in the telescope or these things that we observe in high energy particle accelerators to things that we can directly measure. So very quickly, the Doppler effect. Here's a police car. If the car is coming towards you, the waves that are coming out get pushed together. So the siren appears to have a higher pitch, or in the case of light, it would be shifted to blue. If the police car is moving away from you, then the sound is shifted to a lower pitch because the waves are stretched out, or in the case of light, we would say red. So the light from these distant galaxies is red shifted. That's what Edwin Hubble noted. And the most straightforward explanation of this is that the galaxies are moving away from us, meaning that the universe is expanding. So here's a little picture of the expanding universe. Now, kind of a thing I should disabuse you of. There's a common misconception that, okay, if the universe started as the Big Bang, well, then there's a point somewhere in space, like maybe somewhere like a little past the Andromeda galaxy, there's a point, and that's where the Big Bang happened. That's not true at all. Everything is expanding. The Big Bang happened everywhere. So in fact, the space that fills the universe right now, everything around us, even distant galaxies, All of that was compressed down into a single point, and that's where the Big Bang happened. Every place. The Big Bang was every place at once. So a way that you can think about that is there is no center, if you will. Everything expands. And you can think about that sort of like a balloon. So imagine all of these galaxies on the surface of the balloon. As I blow up the balloon, if this galaxy says, where's the center? Well, the center is not anywhere. Where these galaxies are, the center is, if you will, someplace else. All of these galaxies are expanding, and each galaxy, the recession speed is proportional to its velocity. The further, or say the recession speed is proportional to the distance. The further away the galaxy, the faster it's receding. So if the universe is expanding, it's getting bigger. That means it was smaller in the past. Well, if you extrapolate all the way back, that means the universe started out as a single point. So that was really difficult for a lot of people to wrap their minds around. And in fact, it was a Belgian priest, an astronomer by the name of Georges Lemaitre. And he said that if the universe started off very tiny, it must have had a definite beginning. It had a beginning at a specific point in time, the beginning of time. He called this the cosmic egg or the primeval atom, but the name which eventually stuck was given by people who were ridiculing this model, and they called it the Big Bang as a pejorative. But that was the name that ultimately stuck, the Big Bang. So of course, this is all well and good, but is there any evidence that this actually happened? Well, in 1948, George Gamow, and he's going to come back a little bit later, George Gamow did a little calculation. If the universe was once very hot and very dense, then if we look back far enough, what we're going to see is that very, very hot, dense universe. Because remember, the further back we look, the further into the past that we're seeing. So another paradoxical idea is if I look further and further and further out into space, you imagine like these ever expanding circles out into space, the further out I go, I'm seeing the universe when it was much smaller. So eventually, if I look back far enough, I see this wall of fire, if you will, when the universe was something like 3,000 degrees and it was just everything was bright. Now, of course, that is receding from us very, very quickly, which means it's going to be redshifted by about a factor of 1,000 into the microwave part of the spectrum. Now, in 1948, microwave research was basically non-existent. So Gamow published this paper. Everyone kind of went, oh, yeah, that's nice. No one's ever going to measure that. Until the 1960s. Penzias and Wilson were engineers. They were designing microwave communication systems, and they were trying to track down sources of noise in the microwave part of the spectrum. Anyway, they pointed their telescope, and wherever they looked, they saw this noise everywhere. It's remarkably uniform noise coming from every direction in the sky. They couldn't figure out what it was. They troubleshot all of their electronics. They even climbed into that horn and they cleaned bird poop out of the inside, if that was doing it. They couldn't figure it out. Finally, they went down to the physics department at Princeton, figured maybe there's somebody there who would understand this. And Robert Dicke was there at the time and said, this is what Gamow predicted. This is the cosmic microwave background. And Penzias and Wilson were awarded the Nobel Prize in 1964. There's some controversy over this, that Dicke wasn't also awarded the prize. Gamow, I believe, had passed away by then, so he wasn't eligible to win the prize. So this radiation is remarkably uniform in all directions. Nobody could see any difference until you get to about the 1990s, when the first satellite called COBE was put into space. Once you get above the atmosphere, once you get away from terrestrial noise, they were able to finally detect that this radiation is not quite uniform in all directions. It actually is very uniform, but on scales of about 1 part in a few 100,000. The temperature of this radiation varies. So imagine having 2 points in your room where the temperature disagrees by about 1/100 of a degree or 1,000th of a degree. Imagine the type of measurements you'd need to do that. A thermometer over here and a thermometer over here. Well, this is 78.002 degrees. This is 78.003 degrees. That's the sort of measurement that they were doing with COBE. And they discovered that this radiation is not quite uniform, that it has these little patterns, these little hot spots and cold spots. COBE was followed up with WMAP and then eventually with Planck, which just had higher and higher sensitivity and higher resolution. And this is what the map looks like today. This is an all sky map. That's 360 degrees of the sky aspected onto a flat plane. And you see these little hot spots and these cold spots. And what those represent are the mass distributions that would eventually turn into the first galaxies and galaxy clusters. So the way this works, it's sort of like economics. The rich get richer and the poor get poorer. What do I mean by that? Well, if I have mass which interacts gravitationally, if the mass starts to clump in one place, it has a stronger gravitational pull, which means it's going to tend to pull surrounding material in, which means that that denser clump becomes denser and denser and denser with time. And eventually, that's how galaxies and stars form. Meanwhile, the space in between, all that matter is eventually sucked out by these higher density spots. So what we're seeing here is essentially a baby picture of the universe, 380,000 years after it formed. And this is a snapshot showing just how much structure and how much detail it formed at that time. And that tells us a whole bunch about the composition of the universe. In particular, how quickly this stuff is clumping. It also tells us about the geometry of the universe, the shape and the size of these. So now, let's set all of that aside for a minute, and let's think about something else. Where did all the chemical elements come from, all the elements of the periodic table? Well, this goes back to a paper which was published by Ralph Alpher and George Gamow, remember him? And they also invited a guy named Hans Bethe, who is the lead scientist on the Manhattan Project. He worked out a lot of the formations of elements inside stars. So the three authors on this paper are Alpha, Beta, and Gamma, the first three letters of the Greek alphabet, which is kind of symbolically interesting because it's the origin of chemical elements by alpha, beta, and gamma. So what they did was they took terrestrial results, essentially results from nuclear reactors, calculations based on nuclear physics, and they said, how did elements form in the universe? So there's essentially two different processes, or I should say three different processes going on. First of all, it's what happened in the first 3 minutes after the Big Bang. When the universe was very, very hot, very, very dense, nuclear fusion could occur just for the first couple of minutes. It turns out that the only elements that you can form are the lightest elements. Hydrogen with a single proton, helium, which has 2 protons, and a tiny bit of lithium, which has 3 protons. Anything heavier than that, you can't form in a short period of time. So if it were just for the Big Bang, or what we call Big Bang nucleosynthesis, the universe would be hydrogen, helium, and a tiny bit of lithium. That's it. All the heavier elements formed inside stars. Very, very high temperatures and pressures where you're kind of reproducing some of these conditions of the early universe, except that you're doing so for millions of years or billions of years. You have much, much higher confinement time, and you can keep the density higher for much longer, which means that you can start building these heavier elements. So what we see here, a little plot. At the bottom here, this is our little friend, the atomic number, remember from chemistry. Up here we have the abundance, and this is a logarithmic scale, so each tick on this is a factor of 10. So you'll see hydrogen and helium, which are by far the most abundant elements in the universe. Then you'll see these elements, there aren't that much of them. Lithium was produced in the Big Bang, but a lot of it ended up getting destroyed by cosmic rays, and inside stars it gets broken apart. Inside stars, what you end up forming, carbon, nitrogen, oxygen, good stuff. Life depends on that. And then moving our way down, we get to all of the metals. Iron, there's a lot of iron in the universe. We see a peak over there. And then it goes all the way down. So stars do a pretty good job forming elements up to iron, which is where you can get energy through nuclear fusion. Much of the elements heavier than iron, and you see there's kind of a quick drop off after that, you can produce some of these inside stars. It's a parasitic process. It actually absorbs energy, so it's kind of a wasteful process. You can produce some of these inside stars using something called the S process because it's slow, but a lot of these, especially the heavier ones, have to be produced very rapidly. And the way that these are produced is in supernova explosions, when stars end their lives. And to a lesser extent, some are produced with things like merging neutron stars. I don't really want to get into that. I think I've bitten it off way more than I can chew for tonight. But it suffices to say that we can relate known physics of things that occur in the laboratory to the abundances of chemical elements in the universe. And it tells us about how these elements were forming. So again, the nucleosynthesis is really hydrogen and helium in the beginning, the first 3 minutes of the universe. Nuclear fusion in stars explains most of these from, carbon up to about 40 or so. And then supernovas, merging neutron stars, that's where all these heavy things come from. Okay, so that's the origin of chemical elements. So now let's go back to that expansion of the universe. So Hubble's proposal was that this expansion rate is linear, that the more distant the galaxy, the higher the velocity. If a galaxy is twice as far away, if we double the value of d, then we double the value of v. And then this h0 is just a constant, which we call the Hubble constant, that tells us how fast the universe is expanding. As we got into the 1970s and the 1980s, what some astronomers noted is that distant galaxies were not quite moving that fast. There's a deceleration. So as the universe expands, it's decelerating. Again, totally understandable. If I throw a ball in the air, its velocity slows down, eventually comes to a stop, and then falls back down. That's because of gravity. So that's totally understood. The universe has a mass. It's pulling everything back together. So the universe expands, and there's a tendency for it to collapse back on itself. Totally expected. And if you measure this deceleration parameter, it tells you about the mass of the universe. Fast forward to 1997, we discovered that there's also an accelerating term to the expansion. The expansion is actually getting faster with time. So it's decelerating, but then separately from that, there's also an acceleration term. This is totally unexpected. This would be like throwing a ball in the air, and as it goes up, it goes faster. It goes faster and faster and faster, and it just explodes into space. Totally, totally unexpected. This is completely unknown, unexpected based on the physics that we understood, and it indicates the existence of something called dark energy. All right. So that's the accelerating universe. That's some of the data there. So what you can see is that there's kind of this uptick over here. So again, the downtick is totally expected. That's the deceleration because of the universe's mass. But in addition to that, there's this uptick. So what's happening is the universe is essentially repelling itself. So the Nobel Prize in Physics in 2011 went to Rees, Perlmutter, and Schmidt for proposing this. And kind of the interesting idea is one of the most straightforward explanations of this dark energy is that it's actually Einstein's Lambda. So remember Lambda, that was what Einstein used to cancel out this natural expansion or contraction of the universe. Well, when the universe's expansion was discovered, everybody was, if you say once bitten, twice shy, they just said, well, clearly this Lambda must be zero. It's unphysical. We'll set it to zero. Well, it turns out maybe this wasn't zero after all, just not the value that Einstein thought. And it's actually giving rise to this expansion of the universe. Okay, so let's put this all together. So we can collect all of the evidence. We can look at the motions of galaxies and clusters of galaxies. And just like the motion of the moons around Jupiter tells us the mass of Jupiter, the motion of the moon around the Earth tells us the mass of the Earth. If we measure the speed of stars going around the galaxy, it tells us the mass of the galaxy. And it turns out that galaxies are way more massive than you would guess based on just adding up the masses of the individual stars. So that indicates that galaxies are dominated by something we call dark matter. It's matter which is dark. It doesn't emit light. So it turns out that whatever we see here is only the tip of the iceberg. There's actually a whole lot more matter called dark matter. So now we take the universe's expansion, which has deceleration due to the universe's mass. This independently tells us that there must be a lot of dark matter because the amount of deceleration is too great to be explained by just what we see. But then there's also the acceleration, which tells us that we have this dark energy thing going on. We can look at the abundances of chemical elements. This also tells us about the density of the universe and the composition of the universe. We can do some detailed mathematical modeling of these fluctuations in the cosmic microwave background. How big are they? How dense are they? How large are they? We can also study some old stars and star clusters, which tell us what the universe looked like 10 billion years ago, 11 billion years ago. And that gives us kind of an early picture of what's going on. So anyway, we put all this together, and we can figure out what the universe is made out of. Here's our little pie chart. So it turns out that ordinary matter, or baryonic matter, which is the fancy $2 term, the term baryon means particles like protons and neutrons. So again, this is atoms, molecules, the periodic table, protons, neutrons, electrons, all that great stuff. Turns out to only comprise about 5% of the universe's mass. Wow. So everything we know of, all the physics that we do, everything we see, everything that we feel, everything that we essentially study in the laboratory, other than these motions of stars and star clusters that indicate additional mass, all of that is compressed into 5% of the universe's total energy density. About another quarter is this dark matter. So again, the dark matter is what we see based on the motion of galaxies and clusters, but also the deceleration of the universe's expansion, and also based on how rapidly, remember those little clusters in the CMB, we can see that because there are those clusters, the mass is collapsing very, very rapidly on itself. And that tells us that not only is this dark matter dark, it also has to be cold. What cold means is that it clumps. If dark matter is hot, it spreads out. It's kind of like popping a balloon and the air just spreads out through the room. That would be hot air. On the other hand, if a balloon was filled with water and I popped it, the water doesn't just expand everywhere, it just kind of plops down. So water we would say is cold, whereas air we would say is hot in this sense. So dark matter has to be cold. And that actually narrows down some of the possibilities for what it could be. Things like neutrinos would actually be hot dark matter. So that doesn't fill the bill here. So in fact, dark matter is something that we have no idea what it is. It's some completely unknown particle. And it forms a quarter of the universe and more than 5 times as much of the universe as ordinary matter. Okay, so you add those up, that's still only 30%. The other 70% of the universe is dark energy. And this is this thing which causes the expansion of the universe to accelerate. If we're not sure what dark matter is, we're really not sure what dark energy is. All we know is that there's this accelerating expansion of the universe, and somehow we get there. And one of the simplest ways to explain this is that Einstein's term lambda. So now an interesting thing is if I add up all of these, if I add up the density of ordinary matter plus the density of dark matter plus the density of dark energy, and when I say density, it's like a very contrived set of units. As the universe expands, obviously its density goes down, but you make a correction for that. As the universe expands, you kind of take a bigger and bigger bite of the universe and say how much matter is in this expanding blob. And that makes it a fixed number. If I add the 3 of these, they add up almost exactly to 1. And 1 is a very special value. Let me go back here. 1 is a very special value, and I'm going to get back to that in just a minute. And it's, as far as we can tell, it's exactly 1. It's within about 1%. So is this an incredible coincidence, or is this something that actually comes from fundamental physics? So I thought this was funny. After the discovery of antimatter and dark matter, we have just confirmed the existence of doesn't matter, which has no influence on the universe whatsoever. All right. So a little bit about how we know this. A couple of the different types of measurements that can be done. These are measurements of supernovas. This is measurements of that cosmic microwave background. This is called baryon acoustic oscillations. It's a different type of analysis of the CMB. We can fit all these together, and there's one space where all of these converge, and that's where our matter density is about 0.3, and again, about 80% of that is dark matter, and where this omega lambda is about 0.7. That's the dark energy, and it adds up to exactly 1. And this little diagonal line here that says flat, this is the line for which the total omega is equal to 1, and this is very, very special. So again, I think of this sort of like a detective story. Let's say a defendant is on trial for murder, and there's a bunch of different lines of evidence. You have the defendant's fingerprints, you have the victim's blood found on the defendant's clothing, the murder weapon belonged to the defendant, you have videotape showing the defendant at the crime scene, you have a motive. Now, if I got a good lawyer, I could probably explain any one of those away. Yeah, I can explain exactly why my client's fingerprints were at the crime scene. They were there the day before. They didn't murder the victim. They were just there the day before. Any one of those lines of evidence could be explained away if you had a good lawyer. But if you have all of these different lines of evidence pointing together, the fingerprints, the weapon, the victim's blood, the video, the motive, eyewitnesses, hair and fiber, when you put all of these things together, it's impossible to really argue against that. Because how could all of them be wrong in exactly the same way at exactly the same time? All right. So the big question here, what's the universe going to do? There's a few different models. There's this idea of a universe which collapses on itself. So it gets bigger for a while, then stops, and then comes back down. We call that a closed universe. That's one model. Then we have a model where the universe expands and eventually reaches kind of a stability where it stops expanding. We have one where it just keeps expanding forever. And then we have this one where it expands, maybe slows down for a little while. That's the deceleration, and then starts expanding very rapidly. We believe that this is what the universe is going to do. It's going to be this accelerating universe. So now it's kind of interesting, probably totally coincidental, is this accelerating expansion started about 4 billion years ago, coincidentally right around when the Earth formed. So maybe the universe knows something that we don't know. They're trying to get away from us as quickly as possible. But either way, according to the best evidence we have now, this is what's going to happen. The universe will expand forever and ever, and it will eventually accelerate. So that's where we get to this picture here. So again, there's our cosmic microwave background. Here's the first stars and galaxies. Here's our expanding universe, and we can see the acceleration starting to kick in over here. And then there's this little thing here called inflation. Okay, so what's the deal with inflation? Well, going back to this omega number, remember I said omega appears to be exactly equal to 1. If omega is exactly equal to 1, we have what's called a flat or Euclidean universe. This means that all of our usual geometry ideas come true, like the angles of a triangle add up to 180, parallel lines never intersect, they remain equidistant from one another, all this good stuff. If omega is greater than 1, the universe is actually positively curved. It's kind of like a ball, or another way to think about it, it's kind of like Pac-Man, when you go off one edge of the screen, you come back on the other, the screen kind of wraps around on itself. We would have a closed universe, and the angles of a triangle are actually greater than 180. If the density of the universe is less than 1, then it has what's called negative curvature, or it's curved like a saddle, or it kind of curves up one way and down the other way, and then the angles of a triangle are less than 180. So again, all three of these are possible, but it turns out that according to the best of our knowledge, this omega is exactly equal to 1, which means the universe is Euclidean, the universe is flat. So the Earth is not flat, but the universe is. So why is omega equal to 1? Is it merely a coincidence, or is there some reason why it's exactly that value? There's another interesting question, which is why different parts of the cosmic microwave background appear to have exactly the same temperature. Now, the reason why that's interesting is these points are so far apart from one another that there's no way that light could have traveled from one point to the other in the time that the universe had existed up to that point. So in other words, there's no way for them to get their story straight. Temperature implies some sort of thermal equilibrium, right? If I pour a hot cup of water into a big gallon jug filled with cold water, the water doesn't equilibrate right away. There's going to be kind of a hot kind of thing of water, which is kind of floating around in here. Eventually it'll spread out, but it takes time to do that. Why would different parts of the universe be at exactly the same temperature, to within, parts per in 10,000 or parts per 100,000? Some theories in physics also predict these things called magnetic monopoles, which no one has ever observed yet. Why don't we see any of those? So inflation kind of solves all of these problems. So if the universe started off very small, well, that solves the problem of that contact in the CMB, because the universe was once very small. And then after everything got to mix together, it expanded extremely rapidly, which means that everything that we see in the universe was in fact in contact in the early universe. It solves that problem. The flatness problem is also solved, because if I imagine taking something and crumbling it up like that, this is definitely not a flat surface anymore. But if I were to pull on it and stretch it like this, I flatten it out. And that's what inflation does. It flattens out the universe. It also helps with the monopoles because the monopoles formed before inflation. So if the universe inflates, the monopoles just get separated by large amounts. So inflation would be really, 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 really nice if it were true, but unfortunately, we still don't have direct evidence for it. There are people who are looking for it. One of the telltale signs that it would leave is it would leave imprints of polarization in the cosmic microwave background. So that's what folks are looking for right now, are these polarization patterns. And if those are found, and there's a good chance that we'll find it within maybe the next couple of years, that would demonstrate whether or not inflation has occurred. And again, it would solve a lot of problems in physics. Okay, so I've gone about 40 minutes, so maybe I'll kind of go quickly through this. What happens on very small scales and what happens on very large scales aren't entirely separate from one another. The early universe was very hot, very dense, and very compact, which means the physics at small scales and the physics at large scales were once one and the same. So we need to understand the physics at those small scales. So I'll suffice it to say that on the smallest scales, nature is weird. If you thought dark energy was weird, if you thought general relativity is weird, you've got another thing coming. The universe at the smallest scales is very, very strange. And this is the domain of quantum mechanics. We have things like wave-particle duality. Particles are both particles and waves at the same time. You know, a particle is like a baseball. I can throw a baseball. It has a definite position. It has a definite velocity. It has a definite momentum. A wave spreads out. A wave on the surface of water is spread out. It has a wavelength that has energy associated with it, but it doesn't really have a well-defined position. We don't know exactly where it is. It's kind of spread out. Well, it turns out that photons and electrons and everything else have both wave and particle aspects to them. They do travel in the form of packets or quanta. So when they're created, when they're destroyed, when they're emitted, when they're absorbed in these discrete particle-like packets, which is why we think of them as particles, but they interact with each other like waves. They can do things like interference. Like when two waves hit each other, they can interfere constructively. When the two waves add up, they can interfere destructively when they're out of phase with each other. If they're coming in at different angles, you can get like these weird like moire and herringbone patterns. So things that we think of as particles actually do this. So we have wave-particle duality. We have something called the uncertainty principle. There are things that you cannot measure at the same time. If I measure the exact position of a particle, I don't know what its momentum is. If I measure its momentum, I don't know what its position is, because the very act of measuring that particle disturbs the system. The very act of observing something changes a system. The system has what's called a wave function, which is kind of this nebulous thing which spreads out through space. When I observe that wave function, I collapse it. I cause it to collapse to a completely different wave function. And we can represent these wave functions with these sines and cosines and things like that. The probability of finding a particle at a given location is proportional to the wave function squared. So there's math that describes how these wave functions propagate through space, how they evolve with time if they're left to their own devices. But the very act of observing that causes it to collapse. So if this wave function spreads out, we can have particles in two places at the same time. We can have particles interfering with themselves. And kind of the extreme example was a thought experiment, was this Schrodinger's cat, where if I have a closed box and there's this hammer here, there's a little radioactive atom. If the atom decays, it trips a little lever, causes the hammer to drop, and it releases poison. It kills the cat. So the question is the cat alive or dead? We don't know. And unless you observe the cat, you don't know whether it's alive or dead. And in a sense, it's in a superposition. It's in a state of alive and dead at the same time. There's a lot of issues with this thought experiment. Large macroscopic objects exhibit something called decoherence. But if instead of a cat, if this were an atom, it would be in a superposition. It would be in two different states at once. So now we get to Einstein's greatest blunder. So Einstein thought this was all ridiculous. This can't possibly be true. The universe could not behave this way. Another consequence of quantum mechanics is that everything is probabilistic. There are no deterministic outcomes. When I perform a measurement, I can cause that wave function to collapse in many different ways. I don't know which way it's going to collapse. All I could do is state what the probabilities are. in much the same way that if I roll dice, I can state what the probabilities are that it'll come up this way or that way. So Einstein said, this is ridiculous. God does not play dice with the universe. But it turns out he actually does. All of these crazy things I talked about have direct consequences in the laboratory, and we can actually measure them. These things like particles in two places at a time, particles interfering with themselves, an atom being in two states simultaneously, these have direct measurable consequences in the laboratory. In fact, a lot of my research comes down to this, studying quantum states of materials. God does play dice with the universe. We know that. The universe is very, very weird at the smallest scales. So this brings us to quantum field theory, which actually takes this a step further. And it essentially asks, why is there something rather than nothing? And in fact, if I had a box that was empty, it's not really empty because the box is filled with air. Even if I sucked the air out of there, there could still be electric fields, magnetic fields, gravitational fields permeating that box. It's not nothing. There is something in there. Even if there are no atoms or molecules, there are still fields going in there. There's still energy in there. So something exists inside there. And quantum field theory posits that these fields, things like electric fields and magnetic fields, are actually little particles popping in and out of existence. It's I like to think of it sort of like on an old school TV. If you tune it to a channel where there's no station broadcasting, you kind of see the static. You see the little black and white things popping in and out. That's really what empty space is. It's these little particles popping into and out of existence. And even what we think of as empty space is seething with activity. We don't really see it because it happens at such small scales. It's kind of like asking a fish about the water. And the fish says, what? What's that? Because the fish has been surrounded by it his entire life, has no idea what the water is. So these fields have excitations. We call those excitations particles, but these particles also have wave characteristics, and these interact with each other by exchanging other particles. So this is what happens. These are two electrons that are interacting with each other, and the way that they do that, it's not that they repel each other with a force, it's that one throws a photon towards the other one. So one electron comes in, kicks off a photon, which hits the other electron and directs it away. So these diagrams were first popularized by Richard Feynman. He was quite a character. So Feynman was a really great storyteller and a character. He would go hang out at bars. He learned to play drums. He went to Brazil. He participated in Carnival. Really, really interesting character. So what you see here, and let's go to the next, actually, before that, one more. This was Feynman later in life with his wife, his kids, and his mother-in-law. He actually had a van with these little diagrams printed on it. So it would always be fun because he would drive around at Caltech and people would stop him and say, hey, why do you have Feynman diagrams on your van? And he would say, because I'm Feynman, that's why. And his license plate was quantum on this van. So he's quite an interesting character. So what these diagrams actually represent are nasty, god-awful equations that look like this. So these are the equations of quantum field theory that describe how particles interact with each other. So these are nasty. One of the things about quantum mechanics is that it's not really one thing happening. It's really a whole bunch of different things happening. So when you see an interaction between particles, it's not just this happening. It's actually a whole bunch of different things. So going back to the previous one, these diagrams are all showing the same sorts of things. Particles go in, particles go out. What happens in between looks very different. You have these little loops. You have like a square over here. There's one here that has like a box. The one that is on this slide just shows a single photon. The actual interaction between these two particles is a sum over all these possible interactions. So if you take all the possible diagrams that would have essentially the same inputs and outputs, because the inputs and the outputs are the only things that you can actually observe, if you come up with every possible diagram that would have the same inputs and outputs, so I could put a little circle inside here instead of one photon, maybe there's two, maybe there's three, maybe there's 27, maybe there's 148 photons that are exchanged. Each one of these has a different diagram. Each of these diagrams corresponds to an integral that looks like this. And you would have to sum over all of these possible integrals, and that tells you the probability of an interaction happening. Really, really complicated stuff. The fortunate thing for electromagnetism is that basically each one of these vertices reduces the probability of this happening by about a factor of 100. So these really complex diagrams essentially start to disappear. So that 148 photon interaction would be dropped off by 300 digits, right? 10 to the minus 300. So I wouldn't have to worry about that very much. So that's what makes it possible to calculate these. Anyway, these little things are called virtual particles. So two electrons come together and repel. The reason they repel is there's all of this activity between them. A photon that goes back and forth, maybe an electron-positron pair, maybe a quark pair, maybe a W boson or a Z boson, and all these other particles. Now, these things, it turns out, are real, and you can measure them. And one of the ways that you can see it, if you've ever been sailing, there's this phenomenon where if you have two boats that are next to each other, they tend to drift closer and closer over time. And the reason for that is this boat sitting here is being buffeted on all sides by waves. It's getting hit on the left, hit on the right, hit in the back, hit in the front. But all of these things nominally add up to 0. For every wave that hits you from the left, one hits you from the right. But if the two boats are close to each other, they partially shield one another on those inside faces, which means that the waves coming in from the outside are going to beat the waves on the inside, so they tend to drift closer and closer together. And in fact, this happens. If I take, let's say, two metal plates and put them close together, there's an attractive force between them because these little virtual particles that are pinging against the outsides, but you can't get those virtual particles in between because their wavelengths are too long. This is called the Casimir effect, and it has been measured, and it does agree with the predictions of all of these, that stuff. Do the calculations, and it does predict the experimental results. So to study all of these particles, we have to build very, very large colliders. This is the Large Hadron Collider, which can accelerate particles up to very, very high energies. This is an example of some particles traveling in a path. One of the things you do is you apply a magnetic field. Magnetic fields make particles travel in circular paths. The radius of that circular path tells you about the particle's mass and about its momentum. The direction in which it circles, whether it's clockwise or counterclockwise, tells you whether it's positively charged or negatively charged. So looking at a diagram like this, there's a whole bunch of physics you can get out of here. You can figure out what the masses of these particles are, what the momenta of these particles are. So there's a lot of really interesting stuff that you can do. So we have the particle zoo. It turns out that there are lots and lots of known particles, but many of them are composite particles produced out of a relatively small number of elementary particles, and I'll show you what those are. Even more surprising is that as far as we know, all interactions in nature are described by just 4 forces. The first one is electromagnetism. So by the name, you see electricity, you see magnetism. But almost everything falls into that. Light is an electromagnetic wave. So anything having to do with light, radio waves, X-rays, anything like that is electromagnetism. What about me sitting in my chair right now? What prevents me from falling through? What prevents me from falling through the floor? Well, if you took a physics class, you'd say, well, my butt pushes down on the chair pushes back up on me with an equal and opposite force. We would call that the normal force. We would say that's Newton's third law. But what is that force? Why is there a normal force? Why do I not fall through the chair? Well, the chair is made out of atoms. My butt is made out of atoms. Surrounding those atoms are clouds of negative charges, electrons. So we have the negatively charged electrons in me, the negatively charged electrons in the chair. As these come close to one another, we know that like charges repel. It's actually the negative charges in me coming near the negative charges in the chair, repelling one another. That's an electric force. Electromagnetism describes that. Friction, anything like that, is electromagnetism. It's the interaction between atoms and molecules, and those are electromagnetic interactions. There's also something called the strong nuclear force. This holds nuclei together. The interesting thing about the strong nuclear force is it is very, very short range. It's limited essentially to atomic nuclei. That's why we don't see it in the everyday world. It is stronger than electromagnetism by about a factor of 100, but it's confined to very, very small scale, so we don't see it outside of the atomic nucleus. Then there's something called the weak nuclear force, which is a lot like the strong nuclear force, except that it's weaker by a factor of a couple billion. So about a billion or so times weaker than the strong force. The weak nuclear force, basically where we see that is radioactive decay. So anything that's radioactive and decays, that's the weak nuclear force causing that. Again, it's weak, also short range. And then that brings us to gravity. Gravity, as I said in the beginning, is really, really tough to fit in. So those things with the Feynman diagrams and the mathematics, as nasty as it looks, it works very, very nicely for the electromagnetic force. It works very, very nicely for the weak nuclear force. Strong force is a little bit harder. The problem with the strong force is those vertices, every one of those little points, instead of it making the interaction 100 times less likely, it actually makes the interaction more likely, which means that those ugly, god-awful diagrams with lots and lots of particles interacting are actually the dominant ones. So it's kind of like remember in math, if you looked at those infinite series, if I have like a 1 plus a half plus a quarter plus an eighth plus a 16th, that's the series from Zeno's paradox, it adds up to a finite amount. And in fact, even if I just look at the first couple of terms, it actually gets pretty close to the final answer. So in other words, we say it converges very rapidly. The strong nuclear force is a series that's more like 1 plus 2 minus 3 plus 4 minus 5 plus 6, where it's going up and down and up and down, and the terms are getting bigger and bigger. It's very hard to see where that's going. So the strong force is very well described theoretically. It's just a lot harder to do calculations. And this is where supercomputers really come in to start doing these calculations. Anyway, suffice it to say, electromagnetism, the strong force, the weak force, all fit in very well with quantum field theory. We understand them very well. For the strong force, the calculations are a little more difficult, but gravity does not fit. We cannot fit it to any of these models. These quantum field theory models just don't fit mathematically. Gravity behaves very, very differently. So here's the particle zoo. So pretty much everything that we deal with in nature, here's our electron. The up and the down quarks, these combine together to make protons and neutrons. So 2 ups and a down gives me a proton, 2 downs and an up, that gives me a neutron. So the up quark, the down quark, and the electron, that's atoms, that's molecules, that's the periodic table, that's chemistry. Throw in the photon, that's all of your electric forces, your magnetic forces, chemical reactions, all of that. So 1, 2, 3, 4 particles. That's basically everything we deal with in everyday nature. Then there's this thing called the neutrino, the W and the Z boson. So these are the things that speak the weak nuclear force. So that's all your radioactive decay. Over here is the gluon, which is the mediator of the strong nuclear force. And then there's this Higgs boson, which is the thing that gives particles their mass. So that's it. That's all particles known to science. Everything else is produced by combinations of these. Now, what's interesting here is there are actually 3 generations of particles. So everything you see here, the up, the down, the electron, and the electron neutrino, these have copies. These particles are identical in every way, except that they're more massive. Same charge, same property, same spin, a whole lot of other things. I remember that episode of Seinfeld when Elaine was hanging out with those bizarro people, and there was like the weird Jerry and the weird Kramer. They were kind of like the same people, but they were different. That's sort of what happens here. You have the first generation of particles, which is basically everything we know in nature. But then there's a second generation, which is exactly the same, except a lot more massive and very short-lived. And a third generation, which is even more massive and even less long-lived. These things can only be produced in particle accelerators. A few of them are found in cosmic rays. So why do these things exist? Why do we need them? Why do they exist in the first place? If one generation is all we need for everything in the universe, why are there 3 generations? Interesting question. So everything we know in physics, this is the standard model. This is what's called the Lagrangian of the standard model. This is kind of nasty looking here. This is really horrible stuff. Each of these terms represent matrices that you're multiplying together. But basically all known physics other than gravitation can be described in a coffee cup. So how do we fit gravity into this? So the inspiration from classical physics was that we had these two disparate phenomena called electricity and magnetism, and this thing called light. What we discover if you kind of go into the second year, if you go a little bit beyond introductory physics, what we discover is that all of these are actually manifestations of the same thing called electromagnetism. It also turns out that the electromagnetic force, the strong force, and the weak force are different aspects of a single, more unified force, although you have to go to very, very high energies in order to see that. So are all of these forces aspects of one superforce? So in the case of the strong, the electromagnetic, and the weak, yes, they are. We know that based on experiments at the LHC and elsewhere. Is it possible to fit gravity into this model? That nobody knows. So people like Stephen Hawking have worked on this for many years. There are various models, string theory, quantum gravity, supersymmetry. These are some of the names they've gone under. A lot of math, a lot of theoretical speculation, but so far, no experimental evidence. We're going to have to get to really, really high energies in order to see the unification of these. So anyway, I've talked for an hour now, so I'm going to tie it all together very quickly. We have a pretty solid picture of how the universe developed, just starting from a couple of seconds after the Big Bang, starting from really hot, really dense nuclear fusion and all of that, going into the cosmic microwave background, then into the evolution of stars and galaxies. We know that the universe's evolution has been guided by the very same laws of physics that we can propose in terrestrial experiments. Or another way to say it is we have physics at large scales and physics at small scales. And if we push our experiments to higher and higher energies, we're going to probe further and further back toward the Big Bang, and also to where large-scale physics and small-scale physics ultimately meet. So the big questions that remain, did inflation happen? It would be really nice if it did, but it would be nice if we had evidence for it. Can this inflation be related to subatomic physics? This happened when the universe was very small, so is there something in subatomic physics that relates to how this inflation occurred? 95% of the universe is made of stuff we don't understand. What is dark matter? What is dark energy? Maybe we'll know what dark matter is in the near future. There are some experiments that are trying to detect dark matter particles. So this is something we may be answering in the near future. Dark energy, I think we'll be waiting a lot longer. So can all of these forces and particles be unified, particularly including gravity? Are there any more fundamental forces or particles? Anything beyond the four? Is there what people call the fifth force? Does anything exist beyond that? And then the most speculative of these questions, in the quantum world, these little virtual particles spontaneously pop in and out of existence. Remember, what we think of as empty space is actually seething with activity. These little particles popping in and out. And we know these exist because of that Casimir effect. And there are other things as well. There's something called the Lamb shift, which affects atomic spectra. We know that these little particles popping in and out of existence, we know they exist because they affect the real particles that we can see. Could this be how the universe arose? Could there have been some fluctuation of virtual particles, perhaps in a different universe, that gave rise to our Big Bang? And maybe our universe will eventually give rise to other universes out of these quantum fluctuations. And if so, how did that happen? And that is my talk. So I will go back to the question slide, or the big question slide, and I'll be happy to take your questions. Thank you.
Thanks, Jeremy.
Yeah, thank you, Jeremy.
So we have one question. None of the particles in the standard model are candidates for dark matter. The Large Hadron Collider has found nothing beyond the standard model. No experiments have detected dark matter particles. Could it be that we need a new theory?
A really good question. Okay, so as far as the particles in the standard model, let's flip back to that. So we need particles that have mass. I'm just going to clear up my screen here. So let's see, the quarks, these all interact by the strong force. Anything that interacts by the strong force can't be dark matter because it interacts really strongly. Anything that has electric charge interacts electromagnetically. So that can't be a candidate for dark matter. So that eliminates all of these as well. That leaves us with the particles down here. Neutrinos would be dark matter. They would be, but because their masses are very low, the masses are non-zero but very low, neutrinos would be hot dark matter, which means that they cannot be anything. So what that means is cold dark matter is something beyond the standard model. So yes, if dark matter exists, there is definitely beyond the standard model physics. There are more particles beyond what's here. So in fact, that's one of the things that makes dark matter searches so interesting, is that it basically guarantees that you're going to find something that doesn't fit in the standard model, which means, yes, there might be additional forces. There certainly will be additional particles. So yeah, so that was kind of part one of your question. Yeah, the LHC so far has found nothing beyond the standard model. There are some dedicated dark matter experiments, which recently there is some signals of maybe something, but it's still very tentative. Could it be that we need a new theory? Well, there's a theory called modified Newtonian dynamics. And essentially the idea here is that gravity behaves slightly differently on large scales. And you can try to use this to explain away, say, the rotation curves of galaxies. The problem is there's a lot of evidence for dark matter that goes beyond that. There are some, for example, two galaxies collide with each other. The galaxies themselves can mix in because the matter interacts strongly. Dark clouds right through one another. They just pass right through because they don't interact. And we can actually see from mapping out the mass distribution of these interacting galaxies that the bright matter is kind of the center, but then you can see evidence for these two big clumps of dark matter that are separated. So there's clearly something that is very difficult to explain with something like this modified Newtonian dynamics. There's also the deceleration of the universe, the physics of the cosmic microwave background that don't seem to fit. So I think for that reason, not many people take this modified Newtonian dynamics seriously. There is real mass, and it's something. So yeah, it's a really good question, and yeah, there most likely is physics beyond what we see. All right, so Bob's question, let's see. Fish don't realize the concept of water because they were always in it. Wouldn't they have learned about water when they were in schools? All right, that's a dad joke that I'm going to add to my collection. Thanks for that. All right, other questions?
That seems to be it for the moment, Jeremy.
All right, so everybody's ready for the test then.
Well, I want to thank you, Jeremy. It's extremely interesting and also a lot of information.
Yeah.
So I just want to remind everybody, you can join us every Friday night at 8 p.m. But for our members next week, our presentation is Solar Missions in the U.S. Southwest by AAI member Bonnie Witskill. And thank you for joining us tonight and wishing everyone clear skies.